All right, so now we're in section 4.6. Whoops, I am in the wrong thing. We're in section 4.7, complex zeros of rational functions and polynomials. Now, this is an optional section. It's not actually covered in the course. It is in the book, so I'm just going to make a single video to cover this whole thing. If you're here listening to it, congratulations. Hopefully you find it interesting. So there's something called the conjugate pairs theorem, which we'll go over. And then we can actually try to find a polynomial that has a given certain collection of zeros, and then maybe in general find complex zeros of polynomials just in general. So, okay. A complex variable is a number in the what are called the complex number system. So a complex number, let me go back to the previous slide because it had more space. So a complex number is written in the form x plus I times y. X and y are both real numbers. And I is a sort of just a generic symbol, but what it stands for is that if you square it, you get -1. Okay? So it can't be a real number. I is not a real number, because there is no number that when you square it, you get -1. I just declare that this symbol, if I square it, I get -1. Okay? And now if I take any real number plus any real number times this new symbol, I call it a complex number. You can add them just like you would add anything else. So if I had a plus bi, and I want to add to it c plus di, addition works just like it should. So notice that I have an a plus c, I have a bi, and I have a di, and I can factor an I out of this second term. So at the end of the day, what happened? I had two complex numbers, and when I add them, the part that doesn't have the I, the A and the C, just got added together. And the part that did have the I, the B and the D, also just got added together. Okay, fairly straightforward. You can also multiply them. So what happens if I take A plus BI and I try to multiply it by C plus DI? Well, things just expand like they should. You get A times C plus B times C times I plus A times D times I plus B times D times I squared. But remember that I squared is -1. So what this really is AC minus BD, because this right here becomes -1 times BD. Then from the other two terms, I can factor out an I, leaving behind BC plus AD. This isn't supposed to be obvious or, oh, of course I'll remember this as a formula. My only point is multiplication works exactly the same way as long as you remember that I squared is -1. After that, everything's the same. Okay. So for example, we can compute 3 plus 2i times 6 minus I plus I times 4 plus 7i. This is just a bunch of arithmetic now. So if I distribute out this second thing, I'm going to get an 18 plus 12i minus 3i minus 2i, whoops, come on, back, minus 2i squared. That was just foiling out that first product. If I distribute the I to the second thing, we get a plus 4i plus 7i squared. Now I just remember that I squared is -1. So 18 plus 12i minus 3i, excuse me, plus 2, because the I squared becomes -1, plus 4i minus 7. Now I'm going to collect all of my i's and all of my just numbers. So I have an 18, a 2, and a minus 7. That gives me 13. 12 minus 3i plus 4i gives me 13i. Okay, so we were able to just do that arithmetic. We're going to need to know what the term conjugate pair is. So the conjugate of a plus bi is a minus bi, and vice versa. The conjugate of a minus bi is a plus bi. Why is this kind of interesting? So consider a plus bi times a minus bi. Well, if I FOIL this out, we get a squared plus abi minus abi minus b squared I squared. These exactly cancel, and then the I squared being -1 gives me a squared plus b squared. The i's went away. Okay. So the conjugate of a number, if you multiply it, is going to cancel out all of the i's, all of what's called the complex part. Okay. So in the pair a plus bi, a is called the real part, and bi is called the complex part. So when you multiply a number by its conjugate, you cancel out the complex part and you're left with a real number. This also means instead of starting from this product at the left and ending with this thing on the right, if you think of starting at the right and going to the left, this gives us a way to factor. Okay, so this is an old result. How do you factor a squared minus b squared? Oh, that's easy. It's a difference of two squares, so I do a plus b times a minus b. But now we've actually seen that it's totally feasible to factor a squared plus b squared. Okay, it was a plus bi times a minus bi. You can also see this the following way. B squared is negative b squared. Agreed? So that's negative 1 times b squared. But -1 is exactly I squared. So in the old difference of two squares factoring, we can use this. So if I was trying to factor a squared plus b squared, we've just determined you can call this a squared minus ib squared. And now I can factor it as a difference of two squares, a plus ib, a minus ib, although we tend to write it in the order a plus bi, a minus bi. So you can factor the sum of two squares by turning it into a difference of two squares involving this complex variable I, and now I have it factored using complex numbers that form a conjugate pair. A pair of numbers that are conjugate to each other are what's called a conjugate pair. Okay, so that's the background on how you add and subtract complex numbers and what a conjugate is. So suppose I've got what looks like a plain old polynomial, but now instead of letting x be a real number, I let x be a complex number. This is fine because if you have a complex number like a plus bi, I can square it, I can cube it, whatever, just by doing all the same stuff. Okay, a plus bi squared will work out to be a squared minus b squared plus 2abi. You just have to FOIL it out and then remember that I squared is -1. But the point is the square of a complex number, so it had a real part and a complex part. It's another complex number with a real part and a complex part. And you can cube it, you can fourth it, etc. So if you have a polynomial, you can plug complex numbers into it. If there's a complex number that you can plug into a polynomial and get out a 0, you still call that a 0 of the polynomial or a root. It's just a complex number instead of a real one. Okay. So the most basic theorem in algebra is, I don't want to say basic like it's easy, I mean basic like it's fundamental. It's one of the most important theorems in all of math. Every polynomial of degree at least 1 has a 0 as long as you're allowing complex zeros rather than real ones. Okay, so for example, here's a polynomial, x squared plus 4. You might go, okay, fine, x squared equals -4, no solutions. Alas, there are no real solutions. But there are complex solutions, because this is the sum of two squares. It factors as, x plus 2i times x minus 2i equals 0. In other words, x could be 2i or x can be negative 2i. It has two distinct complex numbers that are roots. Let's check it. Let's take 2i and square it and add 4. Well, 2i squared is 2 squared I squared. What's 2 squared? It's 4. What's I squared? It's negative 1. Plus 4 equals 0. Yes, this is a complex number that is a root of this polynomial. So the fundamental theorem of algebra says any polynomial that is of degree at least 1, so not a constant polynomial, not a degree 0 polynomial, any polynomial of degree 1 has a root that's a complex number. Okay. What that means is, remember, if you have a root of r, so f of r equals 0, then you have a factor, x minus r. So then f of x can be expressed as x minus r times some other stuff. So if f of x is of degree 10, let's just say, it's a complex polynomial. It has a complex root, which means I can factor something like this out. But if this was of degree 10, this is of degree 1, that means this has to be of degree 9. But it's now a polynomial of degree 9, which means it has a root. So I can find something and factor it out. And if this was one root, maybe this is a second root. Then what's this? This has to be of degree 8, and so on and so on. So anytime you have a polynomial of degree n, it can be factored completely as a product of a bunch of linear things, exactly n of them. However, the roots might have to be complex numbers, and the coefficient might have to be complex. So we've been dealing with these polynomials, and we've been trying to factor them, and like sometimes it was like, well, this polynomial doesn't have any roots. Oh well. In the language of complex numbers, every polynomial can be completely factored. However, you might have to deal with complex numbers. Okay. The conjugate pair theorem says if you have a polynomial where the coefficients, in other words, the numbers multiplying the x to the I or x squared or whatever, if all of those coefficients are real, so I don't have complex numbers as coefficients, my coefficients are all real numbers, then if you find one complex number as a root, its conjugate must also be a root. Okay. It's not immediately clear why this second result follows from the first, but it does. Any polynomial function of odd degree has a real root. We already kind of knew this, but we didn't bother to state it. An odd degree polynomial, what's its end behavior? It either goes down on one side and up on the other, or the opposite. Which means, if this is the axis y equals 0, it's got to cross it at least once. An odd polynomial has to have a root. So let's use the conjugate pair theorem. Suppose I have a polynomial whose degree is 5. All the coefficients have to be real numbers, but here are some zeros, 2, 4i, and 3 plus i. Okay, so what are the other two zeros? So 2 is a 0, but that's real, so the conjugate pair theorem, this is, for example, 2 plus 0 times I. What's the conjugate to 2 plus 0i? 2 minus 0i, which is also just 2. That's the same thing. In other words, we got no information. Okay. So the fact that this was a real root means the conjugate pair theorem, while true, does not tell us anything. What about 4i? In other words, 0 plus 4i. What's the conjugate? 0 minus 4i. So negative 4i must be a root. And if 3 plus I is a root, then what must also be a root? 3 minus I. So here are 5 roots. 2, 4i, and 3 plus I were given to us. The conjugate pair theorem told us negative 4i and 3 minus I have to also be roots. It was stated a while back, a degree n polynomial can have at most n roots. So we have a degree 5 polynomial with 5 roots. In the previous slide, in fact, as long as you're talking complex numbers, a degree n polynomial has exactly n roots. So this was a degree 5 polynomial, and now we have 5 different roots, so we're done. Now that we know what the two roots are, we could find what the polynomial is. If 2 is a root, x minus 2 has to be a factor. If 4i is a root, x minus 4i has to be a factor. Since negative 4i was also a root, x plus 4i must be a factor. X minus 3 plus I has to be a factor, and x minus 3 minus I has to be a factor. And then I could have any number I want multiplying out here. But this is the only way I can have a degree 5 polynomial with those roots and real coefficients. Okay, remember the complex conjugate pair theorem only took effect if the polynomial coefficients were all real numbers. Sorry, I need to clear my pen marks up so you can see theirs. So this is just exactly the same argument. Since 4i was a root and we had real number coefficients, negative 4i must be a root. Since 3 plus I was a root, so is 3 minus I. So can you find a polynomial of degree 4 with the following zeros? Negative 2, 2, and 3 minus I. Okay, I'll pause. Go ahead. Well, 3 minus I is a 0, and since we were specifying that we had to have coefficients be real numbers, the conjugate pair theorem kicks in and says, therefore, 3 plus I is a 0. Therefore, I can take all of these 4 roots, and since I'm a degree 4 polynomial, that's all of them, and turn them into factors. Okay, so negative 2 was a root, so therefore x plus 2 is a factor. Positive 2 was a root, therefore x minus 2 is a factor. 3 minus I and 3 plus I were both roots. And then I can multiply by some real number out in front if I want to. Okay, what's x plus 2 times x minus 2? This is kind of obvious as the difference of two squares, x squared minus 4. But this, if you rearrange some terms a little bit, you get x minus 3 plus I, x minus 3 minus I. This is also a difference of two squares factoring of x minus 3 squared minus I squared. Just remember that I squared is negative 1. Okay, and expand out that x minus 3 squared, and now if I simplify, it's x squared minus 6x plus 10. And then I could distribute the x squared minus 4 across the x squared minus 6x plus 10. I'll get a whole bunch of terms to have to collect. There they are. But it simplifies down like this. So while there might be an unspecified non-zero real number hanging out in front A, otherwise it has to look like x to the 4th minus 6x cubed plus 6x squared plus 24x minus 40. So in complex numbers, every polynomial can be completely factored, but that wasn't true in real variables. What is true in real variables is it can be uniquely factored as long as you allow linear factors, in other words, x minus a root, but also irreducible quadratics. These are things of the form ax squared plus bx plus c with no real root. However, what I don't have to worry about is cubic, degree 4, degree 5, whatever. The factors can be broken down to nothing more than linear and irreducible quadratics. So here's an example of a degree 4 polynomial. Can you find the complex zeros of the polynomial function and then write it in factored form? Now, first of all, what degree polynomial is it? It's degree 4. So how many complex roots does it have? 4 of them. They might be repeated. You can have the same root more than once. But what I'm going to do is find a root, factor something out, and then proceed. Okay. So from the previous section, we can use Descartes' rule of signs to try to get a guess about what the zeros that are real numbers might be. If I can find real number zeros, that's nice. So, sorry, let me get back. So let's apply Descartes' rule of signs. We have a positive coefficient, then negative, then positive, then negative, then positive. How many changes? 1, 2, 3, 4. 4 sign changes. So by Descartes' rule of signs, how many positive real roots? It could be 4, but it also could be 2, or it could be 0. Okay. So that's what we have here. They're either 4 or 2 or 0 positive real zeros. Okay, if I take f of negative x, Remember, the original f of x was 2x to the fourth minus 11x cubed plus 13x squared minus 44x plus 20. If I plug negative x in, the even powers don't change, but the odd ones do. So I got a plus here, this stays plus, I got a plus here, and this stays plus. There are no variations in sign now. They're all positives. So there are no negative roots, negative real roots. Okay. All right. The coefficients of f were integers, so we can use the rational zero function, the rational zero theorem, sorry. Okay. Now, we had a 2x to the fourth, and then we ended with a 20, right? Let me just go back and verify. Yes. That means the rational zeros are of the form plus or minus factors of 20 over factors of 2. Now, there's a lot of these. Okay, 20 over 1, 10 over 1, 5 over 1, 4 over 1, 2 over 1, 1 over 1. But also 20 over 2, but that's already 10. 10 over 2, but that's already 5. 5 over 2. 4 over 2, but that's already 2. 2 over 2, but that's already 1. And 1 over 2. These cannot all be roots, okay? I have 2, 4, 6, 8, 10, 12, 14, 16 possible numbers, but it's a degree 4 polynomial that can have at most 4 roots. So these couldn't all possibly be roots, but maybe some of them are. There are no negative zeros. We already knew that, so ignore the negatives. So here's a list of 8 possible roots. If we just start computing, are they roots or not? Let's just plug them into the function. Okay? You will find that 5 is a root. That means x minus 5 can be factored out of this. So now what we have to do is do that long division. Okay. So I need to flip back because I forgot to copy down what the original function was. 2x to the fourth minus 11x cubed plus 13x squared minus 44x plus 20. We already know x minus 5 is going to be a factor. So let's do the division. 2x to the fourth minus 11x cubed plus 13x squared minus 44x plus 20. Okay, this has to be multiplied by 2x cubed. That gives me 2x to the fourth and minus 10x cubed. When I do this subtraction, I get 1x cubed. So I'm going to need to multiply this by x squared. That gives me x cubed minus 5x squared. When I do this subtraction, I'm left with 18x squared. So I need to do a plus 18x. That's going to give me an 18x squared. 18 times 5 is 90. So I get minus 90x. I take my negative 44x and I subtract that, and that gives me a plus 46x. Okay, then I'm going to have to multiply this by 46, and I'm definitely not getting a zero remainder. I made a mistake somewhere. Let me figure out where. $2x cubed, then I have a 10, subtract that. Oh, silly me. This would have been negative x cubed, which means this was supposed to be a minus. Okay, so I end up with a negative x cubed plus that. So this isn't an 18x squared, it's just an 8x squared, so that just has to be 8x. That minus 44x does come down, sorry. Multiply it, and that gets me a 40. Do that subtraction. And get just negative 4. There we go. Now it's all working just fine. And my x is, yeah, negative 4x. So multiply this by minus 4, and then everything cancels out just fine. OK. So having done that division, there's the result. 2x cubed minus x squared plus 8x minus 4 with no remainder. OK. So now what I need to do is figure out, can I factor this? It can be grouped. What I would generally do, actually, is apply Descartes' rule of signs and the rational roots theorem again. Also, in the previous stage, we had a collection of possible rationals, and it was 10, 5, 2, 1, 5 halves, and 1 half. anything that might be a rational root here would have also been a rational root before. So for example, we determined in the previous stage that 10, 2, and 1 aren't roots, but 5 is. But we didn't actually test these. And if we did, we would see that 1/2 is also a root. This means that x minus 1/2 can be factored out, but the fraction might make that a little unpleasant. Multiplied by 2, 2x minus 1 can be factored out, and that's what we see here. Alternately, if you do just spot how to factor this by grouping, factoring by grouping I really don't like going over in teaching because it's a guess and check and you have to get kind of lucky. But if you spot it, there it is, which means it factors like this. Now x squared plus 4, that's an irreducible quadratic. That doesn't have any real roots. However, it does have complex roots. Okay. If x squared is minus 4 and I just take the square root, I know root 4 is 2 and root -1 is I. And I still have the plus or minus because you do that when you take a square root of both sides. So here are our roots: 5, 1/2, plus I, and minus 2i. Which means the factors are x plus 2i corresponding to this root, x minus 2i corresponding to this, x minus 1/2, and x minus 5. So nothing significant changes except you're allowing a different type of number when you're dealing with these complex roots. The benefit is that every polynomial factors completely. The downside is that you have to deal with complex numbers. And Old Westbury sort of has made this decision, we're just not going to make you deal with complex numbers, so this is an optional section. Math with complex numbers, however, is terribly important. There's this misnomer that they're also called imaginary numbers, which makes a lot of students go, no, if they're imaginary, why do I care? It's a bad name for them. They should be called complex numbers. They are very relevant. They are incredibly useful in a great many applications. Electrical engineering and physics uses them all the time. They are just as relevant as real numbers to the physical world. They are. Okay? Just because I have a square root of -1 doesn't mean they are meaningless. It just means that our mental intuition is a little broken. But one thing you get used to very quickly in math is that your intuition counts for a can of beans. Okay? If you can work with the equation, that's what matters. If you can, quote, understand it, end quote, in some sort of squishy intuitive way, that's less important. And complex numbers are where some students start to get this distinction. You can do stuff with equations even if it doesn't seem like it means anything, but it still gives you results that are very useful. For example, polynomials can always be factored as long as you allow complex numbers into the mix. But as I said, not required for this course, so if you made it to the end of this video, congratulations, award yourself a gold star.